Hey all, I hope you're excited. I'm excited. Let's get started with our first proof. Before we start, let's just look at what the general format's going to be. We're going to say something like theorem or some other keyword introducing a theorem. We'll use theorem for now. The name of the theorem that you'd like it to have. Choose good names as always. Colon. The proposition the theorem's going to prove, followed by a period. Okay, that's a vernacular command saying, hey, cock, let's do this. We're proving the theorem. Let's go. And then you say proof, just to get extra stoked. Then you'll issue a bunch of what are called tactics. And these are things that sort of control what Cock believes is true and eventually will let us finish our proof. We succeed. We type QED period, which stands for quod erat demonstrandum. That which was to be demonstrated. That's sort of the breakdown. This is quod, this is erat, and this is demonstrandum. Little free Latin tutorial while we're going. Okay, so that, and then you do a lap around the house or whatever it is, like you celebrate. Right? So that's how it's generally going to go. Let's look at our first one. So let's get in there. Control C, Control Enter. Now, what's going on here? So until now, I've lectured in this sort of adapted view where I've put the response down at the bottom and I got rid of the goals window. By default, you might have just had an extra blank window up in the corner, right? Like up, like in this area, right? And actually, now we're going to start using it. Control C, Control L says, hey, get me back in that nice 3-window mode. What are these windows? So if you look down in the little mini bars here, you'll find not delicious snacks and drinks like you might in a hotel mini bar. In the Emacs mini bar, you'll find information about the buffers you have open. So in this case, it says, oh, well, I'm working on day 11 propositions. And then here, if you read it, it's very small on the screen, but you'll see this says goals, and then this says response. So far, we've really only used the file buffer and response, but goals is about to become really, really important. Now, if your windows ever get messed up, this Control C, Control L gets you back in that state really nicely. So if I do Control X1 and I just look at my file buffer, Control C, Control L gets me right back to this 3-window view. I really like this 3-window view. I think it's really nice. Okay, so goals tell us the current proof state, right? So when proof, no matter where it is, whether it's in Cock or on a whiteboard or on a piece of paper or in a conversation with a person, proof is actually all about state. So the way that a proof works is your goal is to convince someone else of a fact. Well, how do you prove something to them? Well, you have to create a series of state changes in their mind, right? Something happens as you say things to them that alters their view of the world, right? That's what a proof does. So this goals window is showing you Cock's view of the world, and your goal is to manipulate that view using tactics until it agrees with you that whatever you wanted to prove was true. Okay, so what do we see here at the bottom? So there's a line in the middle, and that's just graphical. Below the line is your goal. Above the line will be what's called our context. So let's start it up by running our first tactic. So when I ran proof, Cox sort of realized like, oh, we're really going to do this proof. And then you'll notice it made the goals window really big and response really small. Goals is going to be where the action is at. The goals window is your new best friend. Okay, our first tactic is intros n. So what I'm saying here is like, look, you wanted me to prove this fact that for all natural numbers n, 0 plus n is equal to n. This is the kind of hard-hitting mathematics we're going to do for the first few days. It'll get more interesting, I promise. Right? Adding 0 to a number doesn't change the number. Incredible. Well, to start with, let's say, okay, look, we said this was true for all natural numbers. Let some natural number n be given, right? Give me some natural number n. Great. Now, why is this going to be true? Well, if you recall, well, this is sort of true by definition. Like, let's look back at the definition of plus. Oh, let's look at nat.add, let's say. So if we scroll up, what's it going to do? It's going to match on the first one, and if it's 0, it just returns the second one. So our sort of substitution principle, matching principle says, look, well, look, I know if I run this program a little, this left-hand side should just turn into n on its own. So a tactic that does that is called simpl. could you please simplify my goal? Let's do that again. So, Control C, Control N runs tactic by tactic. So each of our tactics is separated by a period, and we say, we do the next one, the state changes. Let's go back to the beginning. For what are we proving? We know nothing above the line, nothing in our context. We say let n be given. We know about n, and we have to prove that 0 plus our particular n is equal to n. And then we say, well, hey, could you simplify this this goal, please? And then Cox says, sure, I ran it a little, and that 0 plus n, that just turned into n equals n. Now, at this point, we say, okay, Cock, I know you're a stubborn old bastard. I get it. All these like angry type errors, the non-decreasing functions. I know we've had ins and outs. We're frenemies. But even you agree that n equals to n for any natural number n. That's the principle of reflexivity. A quality is reflexive. Everything is equal to itself. Come on, Cock. Don't be mad. Do you agree with me? And then there's this tactic, reflexivity, that says, hey, my goal is a trivial equality. These two things are obviously equal. By obvious here, I really mean syntactically, right? There's just no question that these two things are equal. So you run reflexivity, and then you get something that's like going to become the equivalent of like Pavlov's bell ringing for you. No more sub-goals. Love it. You love to see it. That's Cox's way of saying, yeah, I'm done with the proof. You'd think it could like celebrate more, like it could say something more festive, but no. And then we say QED. Just a quick note. If you try to say QED before you're done, Cox will say, attempt to save an incomplete proof. Like, you're not going to pull one over. I know it seems like, well, I'll just sneak it in early. Doesn't work that way. If you get stuck, you can, of course, just write admitted. Okay. Now, let's keep going. So here's the same theorem. So if for some reason your view doesn't get updated, you can type Control C, Control P, and then it'll make sure you have an up-to-date goal state. If you do that out of a proof, Cox will complain. Now, it turns out you don't need the simple tactic to do this. The reflexivity tactic will automatically do a simple for you, right? So it turns out we could just do this. I really want to encourage you to try to follow along in these on your own. We don't yet have any exercises here, but just doing some of this on your own I think will be really helpful. Okay, we can prove this whole pattern. Like there's a bunch of patterns of these kinds of theorems that sort of say like, well, look, I can do some amount of computation and we're good to go, right? 1 plus n is equal to s of n by the same sort of like substitution argument, right? Like this is s of o. If you kind of run plus now 2 steps, 1 step of recursion, Cox will see what's going on. Right, so let n be given. My goal is to show that 1 plus my particular n is equal to s of n. And again, knowing that reflexivity just will do the simplification for us, Cox agrees, you're right, those two are trivially equal. You might find it comforting, I know that I sometimes do, to do the simple first and just to see it syntactically equal yourself before your eyes. Now, it turns out that reflexivity is a little bit stronger than simple, so sometimes it'll say yes when simple wouldn't have done it for you. But running an extra simple will very rarely actually slow anything down. So if it makes you feel better, you should do it. Okay, one last one. So it's not just plus that we can prove such things about. Here's one about multiplication. For any natural number n, 0 is a left identity. 0 times n equals 0. 0 is a left identity for multiplication. Same pattern. Let n be given. We could say simple, but why bother? I mean, that gets us to 0 equals 0, just as good. But we can also just say reflexivity. And then there you go. Okay, that's enough for this video. In the next video, we'll be seeing some more tactics, seeing some other interesting kinds of propositions. Questions on Zulip as always. There's a lot of stuff to learn on this day. So please be patient with yourself and ask any questions if you get confused. Talk to y'all soon.